Okay guys, let us continue our discussion of the last topic. Let us recap what you did in the yesterday's session. So we had implemented the convolution neural networks using torch modules, a simple convolution neural networks, for the task of classifying animated image faces into one of the two classes, glasses and no glasses. We did that and we got the performance of the model also. Training and test accuracies are 50-50 around, 50% only. So what is the reason that we identified? Once we did the analysis of what is the reason behind the poor performance of the model, one such a reason we identified was very small, quite small data set of only 30 images. So you will not get a proper learning during the training of the model with this small data set. So then we led to the concept of transfer learning. So what is that concept? For such scenarios, if we have the less data and very poor performance of the model on that data, then you can transfer the knowledge gained from some another model which is already pre-trained on another data set of similar type. So that the ImageNet data set, the models which were trained on the ImageNet data set, which is of huge size with 1,000 labels of classification task, we can use by transferring that particular knowledge. What is the meaning of the knowledge? A typical convolution is divided into two blocks. One is the first is the feature block, second is the classification block. Feature block consisting of the convolution layers, pooling layers, right? So which is responsible for generating the features of the given input image. Now these features will be sent to the next part of this convolution architecture, that is called the classification part. So thus this will be divided into two parts, okay, classification part. So when you are reusing or repurposing your pre-trained models for your task of any data set, what you are supposed to do, this lower part, classification part, is need to be replaced with the classification which is suitable for your task, and fine tuning the upper part. What is that? Feature extraction part. So that you can do one of the three strategies, right, that we have seen yesterday. What is the first strategy? Retraining or fine tuning or training the entire feature part. That is one case. Second case is totally freeze that features part, directly training only the classification part. That is strategy 3. In the between these two, we can do learn or train certain features, nothing but certain layers in the feature part and freezing the remaining layers in the feature part. Three strategies are there. According to the concept of, based on the size and similarity of the data set, we can decide which of these three strategies need to be applied for fine tuning your model. That's what we discussed in the yesterday's session. Clear? Right. Now let us moving on to the concept of how to use the pre-trained models. Working with the pre-trained models, now I am going to share you one notebook, practice notebook. It is PSEL TL practice. Yes, it's released successfully. All of you are requested to open that notebook. So for first few minutes of time, I am going to make you to understand how to download, how to work with the pre-trained models. Then one exercise will be given on the task. Keep open this TL practice. Could you please confirm how many of you open, able to access it or not? Right. PSEL TL practice session notebook. Open that. Meet you opening from my side. It's a hands-on session. Okay. What we are doing is we are going to work with how to work with the pre-trained models that we are going to experience. Right. Let me take you the part. Now, yesterday's session, one more point was also discussed. We have seen different types of pre-trained model. LENet, and then VGG16. We had a short discussion of VGG16, a popular pre-trained model VGG16, whose input image size is 224 by 224. We started the discussion, we are going to continue with this. Now we are going to work with this pre-trained model named VGG16, right? In order to, so the thing is we need to load the pre-trained model. So just follow me as it easily so that it will be easy for you to experience with how to use this and pre-trained model. Now what I am going to do is, I wanted to load a pre-trained model. Example VGG16. In order to do this, the first thing is we need the required library, that is called the models from the torch vision, that we need to import first. Import from yes. So import that from torch vision import models. This is the library required to load the pre-trained models. In order to load the pre-trained models, the first step is we need to import the required supporting library. The supporting library is the models which is there available in the torch vision. Right, it's done first. Now, with respect to this model, just call the name of the pre-trained model like VGG16. That's it. Model.VGG16. But this has been stored into another variable. I am storing it into another variable called model. This is my model where I am storing this VGG16. Just run this code cell. Sorry. Okay. Execute it. So models.VGG16 will load your model. Yes. You just check how this model is. Just visualize this model. Just print this model. You can see the information here. Now observe carefully. I said how the typical convolution is defined. It's divided into two parts. One is the feature part, second is the classification part. Now the same thing you can look at here. Thus VGG16 consisting of two modules. One is the feature module. Look at here. This is the feature part. And scrolling down, you can observe one more thing after this average boolean, that is called classifier. Is it clear? It's been divided into two parts, feature part and the classifier part. What is this feature part consisting of? Convolution, ReLU, max pooling, likewise all the layers. VGG16 is a 16-layer model. Among those, whatever the convolution layers, max pooling layers with the associated activation functions which are required and defined for the feature extraction part, you can observe in the features section of the VGG model. Coming down, the outcome of the feature part is an input image of size 7 by 7. Just recollect yesterday's image that I had displayed on the PPT itself. Once the feature part is all the convolution layers were completed, finally you got 7 by 7 by 512. Do you remember the dimension 7, 7, 512? The meaning is total 512 output features, each of the size 7 by 7. So outcome of this feature part is an image of 7 by 7. Then it will be given to the classifier part. What is there in the classifier? Look at here. Linear, linear, linear. 3 fully connected layers. The first fully connected layer, number of features is 25,000. What is this 25,000? Okay, let me come from the beginning. Fine. Look at here. Coming to the feature part, the first is a convolution layer. What is this? 3 input channels. It's a color image it is going to give. Right? 3 is the input channels. 64 is the number of kernels that you want to apply, and each of the kernel size is 3 by 3, and the stride is 1 by 1, and the padding is 1 by 1. if this convolution operation is done on 224 by 224 image, what is the output? Image input size is 224 by 224, right? This is the convolution that you are defining. What is that? 64 number of kernels. Each kernel size is 3 by 3. So, the convolution with the kernel size is 3 by 3 and striding is 1, padding is 1. Apply the formula. N minus F plus 2P plus 1 by S. Remember? What is this N? 224. 224 minus what is this F? F by F kernel size 3. 224 minus 3? 221. 221 plus 1 plus 2P. What is padding? 1. 2P means plus 2. So, what is the value? By striding is 1. What is the value? 224 minus 3, 221 plus 1, 222 plus 2P. P is 1, again 2, 222 plus 2, 224. By stride equal to 1, 224 by 1 is 224. So, what you got again? The image, feature map with the same dimension. So, it is easy for you remember, if the kernel size is 3 and stride is 1 and padding is 1, then input shape remains as it is even in the output feature. How many features it is going to get generate? How many filters you had applied? 64. So, 64 output features you will get of the size same 224 by 224 because you had applied the kernel size 3 by 3, striding is 1 and padding is 1. Apply the formula, just apply the formula. N minus F plus 2P plus 1 by S. You got the same value. It's easy to remember. If the kernel size is 3 by 3, striding 1 and padding is 1, input image size remains the same. Additional number of kernels will be added. Okay, this is the outcome of the first convolution. Then it is given to the another convolution of the same parameters. So, what is the output of the second convolution? Again same 224 by 224, correct? But the number of output channels 64, done. Next max pooling is applied. What is this max pooling? Kernel size is 2, stride is 2. So, it will half the image. So, 224 is going to be half. What will be the value? 112. You just recollect the picture which I shown in the yesterday's session slide. After completing the first convolution block, you got the original input image 224 got converted into the 112 by 112, correct? How many features it is going to generate? 64. Thus, with all these convolutional blocks, this one, second one, third one, fourth one, fifth one, what is the image shape that you are going to get? 7 by 7, right? But how many features? 512. Here you had applied 512 kernels in the last convolution layer. So, what is the shape you are getting here? 512, comma 7, comma 7. So, if you multiply these three, what is the value that you would get? 25,088. Once this part is done, then it is to be flattened. Once the flattening is done, then you can connect it to the fully connected layer with the two parameters, input features and output features. The first fully connected layer with input parameters which is equivalent to the flattened dimension of its previous feature mapper layer. Done. So, this is the first. Now, it is connected to the 4096 hidden units of the network. In the second flattened, second linear layer, fully connected layer, this 4096 is the input feature, again connected to the 4096 of the hidden layer, and the last fully connected layer, This 4096 will be the input features. You can see, look at here, how is the parameter in underscore features, input features of the linear layer, out underscore feature, output features of the linear. Now it's got connected to what is the value? 1000. Why it is 1000? 1000 class classification task. ImageNet dataset is a 1000 class classification task. This is the model trained on that data. Is it clear? Are you able to understand this one? Right. Now, let me take you deeper into this one. So, the model will give you this part. You can use the different methods and the technique also. Model dot features. Can you see the output? What it is displaying? Only the first feature extraction part of the model. Model dot features will give you the only the features of the model. Okay? Maybe I can do it in the same cell, but you guys do it in different cells so that it will be easy to refer back. So, model dot classifier, second section I am calling. The attribute model dot classifier, if you call, you will get only the classifier information. Pre-trained model will be divided into two parts. One is the feature part, second is the classifier part. So you have to remember that this is how you can visualize and see this one. Okay? Model dot classifier will give you the classifier information. Classifier of 0, what it will give? The first module, nothing but the first layer. Okay? It's a linear layer. Now, the thing you need is, look at here, this okay. Now, I wanted to see the model parameters. Model parameters. Can you look at here? Model parameters. I wanted to see what is the meaning of parameters. What are the weights and biases of this model VGG16 I wanted to look at. So it is iterable variable. I need to loop over this one by enumerating this. So what I am doing is, instead of displaying directly for name comma parameter in model dot parameters, now I am displaying the name of the parameter and parameter data, both. What happened? Okay, this named, you are supposed to use named parameters. Look at here. Now, this is important thing, so that you can understand what is the meaning of freezing layers. Just have a look on the output of this result. Can you observe here? These are the weights. Look at the weight, what is there here? Requires gradient equal to true. Notice this one. And look at the weights. How are the weights? These are the weights and these are the biases. Two things are there. Bias, how are the biases? Initialized to zeros. How are the weights? Random weights. Look at, how are the weights? Random weights. Okay. Now, for the next time, just listen, observe what I am doing. Once again, I loaded this image. Just have a look on this one. The weight value, first weight value is minus 0.0204, right? So I'll run this code cell again. Every time I'm getting the same, first value is the same. Okay? I just want you to notice an important thing so that I can, yeah. Okay, same value. Let me reload the model. This code cell I'm running again. Loading of the model VGG16 and running this code cell again. displaying the parameters. Now, just have a look on these values. First value, just cross check the first value. Yeah. What is that? Did you identify it? It's a different from the earlier one. But all the times, if you observe, these are the weight parameters. And what about the biases? Now, what is your conclusion? Can you say? There is an important point to be noticed. When you load the model, pre-trained model, every time it will create and loads a new VGG model, meaning that weights and biases will be random values. Parameters were initialized with the random values and the biases will be initialized to zeros. Got the point? But what you need to do actually, if you wanted to apply the technique of transfer learning, you want the model which is already been pre-trained on some other data set. What does it meaning of pre-trained? Learned parameter values you need, not the initializations. Got my point? Already learned parameters you need. So the thing you need to do is, here is the modification you are supposed to do. Just come to this part. What I did it here, models.vgg16. This statement is loading the model VGG16 with random initial weights. That's wrong. Now I am changing the comment line. Look at here. Load, yes, exactly is this one. Load a pre-trained. Earlier what I did is just I load a model. Now I wanted to load a pre-trained model. So for this what you are supposed to do is, you need to set the parameter pre-trained equal to true while loading the model. Just do that and run the code. Here you are getting one warning message. So pre-trained is deprecated. So suggesting you use weights. You can use either pre-trained or weights. As long as this pre-trained is working, you can use. Otherwise, use the parameter weights equal to true. Once you did this, now run this code cell displaying the parameters and the weights, biases. Display the weights and the bias values. Again load the model, pre-trained model, and display the bias and the weights. Did you identify the difference? The value you are getting is minus 5.5317. Every time when you are, so repeated execution. Again load the VGG16 with the pre-trained equal to true and come to this part and run this code cell and observe the value, parameter values. Hope you noticed the difference. Now you are getting the consistent values, correct? Identified? Now what the values, weights and the biases you are getting are consistent, which are the pre-trained. Remember this. So when you are loading a pre-trained model for your transfer learning task, you are supposed to set the parameters equal to, pre-trained equal to true when loading the model. Accordingly, you have to take a decision. Fine. Just have a look on this. This is about the weight. Just have a look on this biases also. How was it earlier? Initialized to zeros. Now, some bias, updated bias are there, meaning that these are the parameters of the pre-trained, well-performed model. Correct? Okay. So, I cleared one step, how to download a pre-trained model. The second thing is how to freeze the layers. This is what we need for when you are working with a pre-trained model. Correct? Have a look on this one. I said requires gradient equal true. What is that? This is the parameter or the property which enables these weights to be updated. These are all updatable. So these parameters are accessible to you in an updated mode. If you want to freeze the layers, nothing but the features. What is the meaning of freezing the layers? You don't want the parameters of those layers to be updated during the training. How will you make it? The parameters, you can see this, named parameters will give you. You need to freeze that. So this is the property you are supposed to set. So set the requires underscore grad equal to false. Then your layers will be frozen, right? So when you are doing this part, in order to set this one, I am just clearing these values, clearing the outputs for my convenience. So for parameter in modal dot parameters, what is it? Parameter dot requires grad equal to false. This will help you to freeze the layers. So in order to freeze the layers of any pre-trained model, you need to set the parameters that requires gradients equals to false. Then those labels, those parameters will be frozen. So once you run this code cell, again do the execution of this part. Now you can see the difference. Can you tell me what is the difference? So once these layers are frozen, getting the point? Again, see the parameters, how they are looking, and tell me the difference that you notice. These are my weight parameters, and these are my weight parameters. Look at here, biases, this one is bias, before is the weights. Can you identify the difference when you froze the layers, the convolution layers parameters? Guys, have you executed? Okay, do that part. Freeze the layers first. How to freeze the layers? Modal dot, for each of the parameter in modal dot parameters, that parameter dot set the attribute requires gradient equal to false. Meaning that you are freezing all the layers of the model. What is the meaning of freezing all the layers? Means you are disabling the updatable property of the layers parameters. That you can cross check by running the above code cell again, displaying the parameters. This code cell, this part. Name comma parameter in modal dot named parameters, display print name and parameter. Now you can notice one important thing which I highlighted in the earlier code cell. You cannot find that the attribute requires underscore gradient equal to true, which you already which you got it in displayed in the earlier code cell. Meaning that now these parameters updatable property is disabled. Meaning that if you use these parameters for your data set, in the case of transfer learning, these parameters will not be updated. Okay. This happened for both the cases. What is that? Two sections are there. One is the feature section and classifier section. So for entire model, what you did is done for the entire model. Model dot parameters. If you want to do it for the specific part only, model dot features dot parameters. What does it mean? You are freezing the convolution layers parameters only. You are freezing the convolution layers of the model only. Those parameters are only going to be frozen. If you wanted to make these are trainable and want to freeze only the feature layer parameters, not the features are, sorry. What is that? Second part, classifier. Okay. So instead of features, supposed to use classifier. This is enough knowledge. I told you how to see these parameters also. This you can have a look at it. In the classifier, you will get all these different layers in the classifier defined in the classifier itself. I am running this code cell again. In my VGG16 model, there are 6 classifier modules are there. So when you are using now the next task given to is whatever the data set that you had executed for implementing the classification of animated faces for glasses or non-glasses, the same data set is need to be executed. Same task you are going to do with the transfer learning of this VGG16 in order to boost up the performance of that model. Okay? With that case, you got only 50% of training and test accuracy. Now you are going to use this knowledge to that small data set. Now analyze which of these 3 strategies now you are going to apply for this scenario. We'll stop it here. 3 strategies we discussed. One is training the entire convolution part along with the classifier part. That is strategy 1. Strategy 2 is few layers are frozen and few layers are keeping trained along with the classifier. Third strategy is freezing all the convolution layers and only classifier is to be trained. Now which among these 3 strategies will be applicable to our scenario of a small data set? Strategy 3? Right, correct. You no need to retrain this. So when you are going to solve that task with this transfer learning of using VGG16, the feature part layers to be frozen. I told you how to freeze the layers. So the classifier has to be modified, second point. What modification you supposed to do? What is the last layer in this classifier of predefined VGG16? Output features is 1000, meaning that there was 1000 classes in the imaginary data set. But how many classes in your data set? 2. What is the 2? Number of classes that you are getting from there. So this parameter, so the last layer of classifier of your model is need to be replaced with another new layer, NN linear layer with this output features is 2. So your problem will get solved. Done? Will you do that exercise? Okay. I'll release that exercise for you and I'll evaluate in the night and tomorrow. Because you guys are interested, so this is assignment. PSEL TLL assignment. I'm releasing it and you can do it experiment at your home